All right, I got a couple of requests to see the derivation of the linear air resistance velocity as a function of time equation. So the situation is that we have something falling subject to gravity, and there is the air resistance force pulling up on it or resisting its friction of a sort. And they always write the drag force with the negative sign in front of it. And the issue here is just be careful. When you're actually setting up Newton's second law for it, you want to write it as mg minus kv equals ma, regardless of what signs you see in the problem. And of course, the differential equation that we want to solve is mg minus kv is m dv dt. Now we're going to solve this by separation of variables. What that means is we're going to get dt stuff on one side and dv stuff on the other. So when we do that, we're going to end up getting dt over m equals dv over mg minus kv. And at this point, we're going to do a u substitution. So I'm going to let u equal mg minus kv. Now remember, this is a constant. So when we take the derivative to get the du term, we're going to end up getting negative k dv. And when we simplify that out, that's going to be negative du over k equals dv. So let's put those expressions back into our differential equation, and we have dt over m equals negative du over u with this k on the bottom. And I'm going to bring that k over to the other side, so we end up getting k over m dt, and I'll put the negative sign here too, equals du over u. Now what I'm going to do is I'm going to take the antiderivative of both sides. And the trick here is the way I put the integration constants into this problem. Now one thing I neglected to tell you is that v at time equals 0 is 0. And that's the fact that we're going to use. That initial condition, as it's called in physics and in math, is the thing that's going to allow us to eliminate our integration constant. So when we take the integral on the left side, we're going to get negative k over, we're going to get negative k over m times t, and on the right side we're going to get the natural log of u. Okay, and I'm going to add the integration constant right here. So now we're going to do something a little weird with the substitution that you might not have seen in your math classes. We're going to actually substitute to get rid of the c now. So I know that u is mg minus kv, and that means u of 0 is just mg. So let's just substitute that in right here. So we're going to get c plus 0, because t equals 0, equals natural log of, and we have mg minus k times 0. So c ends up being the natural log of mg. So that's going to give us here natural log of mg minus k over mt equals ln u. And I can actually go further with this. Let me just zoom this out just a little bit. And then we're going to end up getting here that the natural log of, I'm going to rearrange this equation just a little bit, the natural log of u, okay, minus the natural log of mg equals negative k over m times t. Let's keep going here. I'm going to use a log rule. The log rule that I'm going to use is ln of a minus ln of b equals ln of a over b. So that's going to give me the natural log of, and let's just get rid of that u again, sorry. It should be mg minus kv over mg equals negative k over m times t. Finally, we're going to take e to the both sides, and that's going to give us mg minus kv of t over mg equals e to the negative k over mt. When we actually do the algebra, there's a couple of steps that I want you to do on your own. You're going to get that v of t equals mg over k, 1 minus e to the negative kt over m. Couple things. Notice that as t goes to infinity, v goes to mg over k, which is terminal velocity. V of 0 is 0. And when you take the derivative of this, you're going to get that the acceleration is just g e to the negative kt over m. So what I want to wrap up with is the graphs. So v as a function of time is going to end up being, it starts at 0, and then it actually approaches as its limit mg over k, which is just terminal velocity. Acceleration as a function of time is going to start off as g, and then it's going to exponentially decay in time like that. So that's a video that should show you how to derive everything. My goal for you is that you're able to do it a little faster than I did it here because I was actually talking through it. So I hope that was helpful.